Hello, good evening, sir.
Yeah, hi Sika, good evening.
Thank you so much, sir, for sharing.
Yeah, it's okay, no problem. Okay, so let's wait few minutes, then we'll start. Okay, so let's start gradually. So today actually we'll be discussing some the rest of the topics of transition state theory, and then we'll be discussing some of the important expression of collision theory, and then I'll go to the enzyme kinetics part. Okay, so let's start. Let me just share my screen. Okay, so TST. So last class we are discussing. We are starting TST. So in transition state theory, I have said that the main assumption or approximation is that first the reactant molecules have to come together or interact together to form an activated complex or transition state. Then from the activated complex or transition state, the product molecules will form. So let's say from A plus B to an activated complex, let's say AB dagger, double dagger. Then from activated complex, the product molecules will form. And the second assumption is that there is a pre-equilibrium between the activated complex and the reactant molecules. So there is an pre-equilibrium. So this is the main assumption of transition state theory. Now, so the rate constant for this chemical reaction according to the transition state theory will be, let's say rate constant is K. K will be just KBT divided by H times K double dagger. Now what is K double dagger? K double dagger is the equilibrium constant between the activated complex and the reactant molecules. That means for these two, this is the equilibrium constant. Now from this expression, we also know that the any equilibrium constant from thermodynamics, we know that the K double dagger will be, we can write down the K double dagger as minus it exponential minus d delta G double dagger divided by RT, right? Now delta G is the free energy of activation. Free energy of activation. That means from, let's see, if we just draw this in a schematic diagram, this is reaction coordinate, and along the reaction coordinate the reaction is happening, and this is y-axis is energy. Now if you draw this diagram, this is reactant molecule, this is product molecule, and from this step reactant molecule to activated complex, the change in the free energy is the activation free energy, the free energy of activation. That means delta G double dagger will be free energy of activated complex minus free energy of reactant molecules. This is delta G double dagger. Now from transition state theory expression, like from this expression, the rate constant expression, the pre-exponential factor is temperature dependent. And how it is depending upon temperature? It is the pre-exponential factor proportional to temperature. So this is important. Like for TST, the rate constant or pre-exponential factor of the rate constant is proportional to temperature. Okay, now we also know that there is an empirical relation, what we call the Arrhenius equation. So according to the Arrhenius equation, so rate constant of any chemical reaction can be fitted by this expression, like rate constant equal to A times exponential minus EA divided by RT. Okay, now here A is the pre-exponential factor. Now in the Arrhenius equation, the pre-exponential factor, that means A, is temperature independent. Okay, so this is important. And here EA is the activation energy. That means from like difference between this energy and this energy, this is EA, activation energy. Now what is the relationship between the activation energy EA and like enthalpy of activation delta H double dagger, or the internal energy of activation delta U double dagger, etc. So first equation from TST we got K equal to KBT divided by H times exponential minus delta G double dagger by RT, and second expression we got K equal to, like form Arrhenius equation, which is K equal to A times exponential minus EA divided by RT. Okay, now if you just take the logarithm of both sides with this in these two equations and take the time derivative, a temperature derivative. So let's say from first equation number 1, if you just take del ln K by del T, which will be the 1 upon T plus, so K double dagger, this is K double dagger, right, equilibrium constant. Now we know from thermodynamics that d ln any equilibrium constant by temperature, if we take the derivative of ln any equilibrium constant with respect to temperature, we will get delta U double dagger divided by RT square. Okay, so from thermodynamics we know that. So that means here we will get delta U double dagger divided by RT square. Now from equation number 2, that means from Arrhenius equation, we will get del ln K by del T equal to just EA divided by RT square, right? Now just compare these two equations. Let's say this is equation number 3 and let's say this is equation number 4. By comparing equation number 3 and equation number 4, we will get 1 upon t plus delta u double dagger divided by RT square equal to EA divided by RT square, right? Now RT square common, so delta u double dagger plus RT equal to EA divided by RT square. Like from this equation you can get the relationship between the activation energy and the internal energy of activation, which is delta u double dagger. So EA will be delta u double dagger plus RT. Okay, now we also know from thermodynamics that the enthalpy or H equal to U plus PV, right? H equal to U plus PV. Now the difference of enthalpy, so delta H equal to delta U plus P delta V, let's say at constant pressure. Now for ideal gas we know PV equal to nRT, so P delta V will be equal to just delta nRT. Okay, so delta H will be equal to delta nRT. Now we will use this equation in our TST expression. So delta for our activation case, like for this step, so for this step, right, from activated complex and the reactant molecules here. So for this step, delta H double dagger will be equal to delta U double dagger plus delta N double dagger RT, right? So we'll use this equation here. So delta U double dagger will be delta H double dagger minus delta N double dagger RT. So delta U double dagger will be delta H double dagger minus delta N double dagger RT. So our activation energy EA will be, so let's just replace this delta U double dagger with this expression. So EA will be delta H double dagger minus delta N double dagger RT plus RT. So EA will be delta H double dagger, so minus, if you take RT common, so it will be delta N double dagger minus 1. Okay, so this is the expression between the activation energy. This is activation energy this delta H double dagger is the activation enthalpy of activation, R is the universal gas constant, T is the absolute temperature, and delta N double dagger is the molecularity, difference of molecularity. That means the number of molecules at the activated complex minus number of reactant molecules. So delta N double dagger will be just number of molecules at activated complex minus number of reactant molecules. Okay, now that means the delta N double dagger is basically the molecularity difference of molecularity. So this is an important relationship. Now So in our original TST expression, we know that the rate constant K equal to kBt divided by H times K double dagger, right? K double dagger is the equilibrium constant between the activated complex and the reactant molecules. Now just replace this kBt divided by H times K double dagger, we can write down as free energy of activation by RT. Then again we know that the kBt divided by H times delta G double dagger. Delta G is the activation free energy, so we can write down as delta H double dagger minus T delta S double dagger divided by RT. So it will be equal to kBt divided by H times exponential delta H double dagger by RT, then exponential delta S double dagger divided by R. This T and this T will cancel, so it will be R. So just make some rearrangement. kBt divided by H times exponential delta S double dagger by R times exponential minus delta H double dagger by RT. Okay, now just replace delta H double dagger with this equation. So it will be just kBt divided by H times exponential minus delta S double dagger by R times exponential minus delta H double dagger. From this equation will be EA plus RT times delta N double dagger minus 1, right? EA plus RT times delta N double dagger minus 1 divided by RT. So it will be equal to just kBt divided by H times exponential minus delta S double dagger by R times exponential minus delta N double dagger minus 1 divided by RT, then times exponential minus EA by RT. So in short, we can write A as a function of temperature, exponential minus EA by RT, right? K equal to. So this is the I-ring equation. Now the important thing is that in the I-ring equation, this the pre-exponential factor, this is pre-exponential factor, right? So pre-exponential factor has the particular form AT is kBt divided by H times exponential minus delta S double dagger divided by R times exponential minus delta N double dagger minus 1 divided by RT. So this is the particular form, and this is important. Often in numerical questions, generally people ask this expression to solve some maths. So here you can see the pre-exponential factor is temperature dependent and it is proportional to temperature, like this temperature. But in the Arrhenius equation, pre-exponential factor is temperature independent, right? So this is the important form. Here delta S double dagger is the entropy of activation. That means the entropy corresponding to the activated complex minus entropy of reactant molecules. Delta N double dagger, we know that it is the molecularity difference, that is the number of molecules in the activated complex minus number of reactant molecules. Now let's say in some numerical questions you have asked that for a bimolecular reaction, for bimolecular reactions. So from TST, what will be the delta N double dagger, right? Like bimolecular reaction means that there are two types of reactant molecules. So let's say, so reaction scheme we can write A plus B to P, let's say. So in TST we first know that these two reactant molecules will come close together and then it will form a activated complex AB double dagger, right? And then from activated complex product molecules will form. So what will be the molecular difference here? Delta N double dagger will be the number of molecules participating at the activated complex. So activated complex is a one complex molecule, right? That means so there is only one molecule at the activated complex, so one complex molecule. Now minus number of reactant molecules. Now there are two types of reactant molecules here, so it will be just 2. So delta N double dagger will be -1 for bimolecular reaction. Similarly for trimolecular reaction, tetramolecular reaction, you can just calculate. So 1 minus 3, 4 like this. Okay. So this way you can compute the delta N double dagger. Then you can put the value of delta N double dagger here. And if you know the value of delta S double dagger, that means the entropy of activation, you can compute the pre-exponential factor. Okay. Now another important topic related to the kinetics is the collision theory. So collision theory actually came before the transition state theory. So in collision theory, actually the first assumption was that first the reactant molecules will collide with each other and the product molecules will form. So by collision, the energy will transfer between different reactant molecules, and by this way the product molecules will form. So let's say so A and B molecules will first collide with each other and then the product molecule will form. Now I will not discuss in detail the collision theory. I'll just write down the last expression. So basically so in our initial collision theory, first the approximation was just the reactant molecules will collide with each other and product molecules will form. So the rate constant will be just equal to the frequency of collision, right? The rate constant of any chemical reactions should be equal to just the frequency of collision. That means the number of collisions which are happening per second, per unit time between the reactant molecules. Frequency of collision. Frequency means per unit time number of collisions happening between the reactant molecules. So there is no now there is no any energy criteria or orientation criteria here. Only the approximation is that first for product molecules to form, the reactant molecules have to collide with each other. So that's why the rate constant is equal to the frequency of collision. But next the assumption is that no in experiment actually the rate constant is often smaller than the frequency of collision. So to explain this, we have to impose another restriction on the collision theory, and that is the energy criteria and the orientation criteria. Energy criteria. So energy criteria means not all collisions are effective collision or reactive collisions. That means not all collisions can form the product molecules. Only collisions between the reactant molecules where, so let's say this is A molecule is coming and this is B molecules. is coming this way. Now, not all the collisions between the A and B molecules will not be the reactive collisions and will not be effective to form the product molecules. Only those collisions where the energy along the line of collision means when these A and B molecules will come close together, so there will be line of collision means like this. So along this line of collision, that means this, like this A and B molecule will collide. So along the line of collisions, if the energy is greater than some kind of activation energy EA, then only those collisions will be the reactive collisions. So only those collisions where the energy along the line of collision is greater or equal to the some kind of activation energy EA, then only those collisions will be effective to form the product molecules. So this was the first criteria. So this is energy criteria, and second one is the orientation criteria. The orientation criteria means so in 3D, so these are all like hard sphere type of molecules, like a hard ball type of, but in real space or in reality, the molecules have some conformation or geometry. So in 3D space, molecule have some conformation. So reactant molecules have to have some appropriate orientation or conformation to form product molecules, to interact efficiently and to form product molecules. So that is the orientation criteria. So orientation criteria says the reactant molecules have to come close together with a particular or proper or appropriate orientation. So with these two criteria, that means energy criteria and the orientation criteria, the modified rate constant now will be frequency of collision, that means collision frequency, times the fraction of molecules for which the fraction of reactant molecules for which the energy along the line of collisions is actually greater or equal to the activation energy EA. So this is the fraction of molecules having energy greater than EA. So this is with energy criteria. So now the rate constant will have two terms. First term is the collision frequency term, and second one is we have to impose this energy criteria. That's why we have to just take account the fraction of reactant molecules having energy greater than EA. Okay. So let's write down the rate constant. So K will be frequency of collisions. We know that the frequency is pi r square times V AB average times N. So this is the collision frequency. So this is the pi r square is the effective volume, where, okay, let's write it down. So this is the part from collision frequency. Collision frequency. Now R is the sigma A plus sigma B divided by 2. Now what is this? Let's draw it here. This is A molecule, this is, let's say, B molecule, and the A molecule diameter is, let's say, sigma A. B molecule diameter is, let's say, sigma B. So R is like this distance. That means sigma A, this distance is sigma A divided by 2, and this distance is sigma b divided by 2. So total distance will be sigma a plus sigma b divided by 2, right? So r is the effective radius, sigma a plus sigma b divided by 2. Sigma a is the diameter, this is the diameter, it's important, diameter of a molecule. Sigma b is also the diameter of b molecule. So then VAB is the relative velocity. Average relative velocity between A and B molecule. Average relative velocity. Now it has the particular form root over of 8 kBt divided by pi mu, where kb is the Boltzmann constant, we know, T is the absolute temperature, and mu is the reduced mass. Okay, and mu has the particular form Ma Mb divided by Ma plus Mb, right? So this is the expression of collision frequency times n. N is the Avogadro number. Then we have to just consider this term, the fraction of molecules having energy greater than Ea. So it will be a Boltzmann factor. That means exponential Ea minus Ea divided by RT. Okay. Now let's write it down clearly. So the from collision theory, the rate constant k will be equal to pi r square times average relative velocity times Avogadro number times exponential minus Ea divided by RT. Now if you write down fully, it will be pi sigma A plus sigma B divided by 2 square, then VAB average equal to root over of 8 kBt by pi mu times n times exponential minus Ea by RT. Okay, now if you just write down this as A as a function of t, so it will be just A as a function of t times exponential minus Ea by RT. A is the pre-exponential factor. Okay, now look at carefully. So from collision theory, the pre-exponential factor At is proportional to root over of temperature, right? So this is important. So the three things that are important. So first one, from Arrhenius equation, pre-exponential factor is temperature independent. Now from TST Eyring equation, pre-exponential factor is temperature dependent and it is proportional to temperature alone. And
So
third,
please repeat last two lines.
Yes, so we have discussed from Arrhenius equation, any rate constant we can write down k equal to A times exponential minus Ea divided by RT, right? This was the Arrhenius equation. Now from Arrhenius equation, this is the pre-exponential factor. Now this is temperature independent. So that's why I am writing down Arrhenius equation. Pre-exponential factor is dependent upon temperature to the power 0. That means temperature independent. Temperature independent. Now from TST Eyring equation, transition state theory Eyring equation, we have write down previously like this. So Eyring equation, this was the Eyring equation, and the pre-exponential factor A as a function of t, it has this particular form which is temperature dependent now, and it is dependent as a proportional to t here, right? So At is proportional to now t. So that's why I'm just writing from Eyring equation, transition state theory Eyring equation, At pre-exponential factor is temperature dependent and is proportional to temperature. Okay, now third is the from collision theory. Now in collision theory, this is the expression of pre-exponential factor like AT. Now from collision theory also, pre-exponential factor, we can see it has the temperature term, right? So it is dependent upon temperature, but AT is now proportional to root over of temperature, right? So in collision theory, the pre-exponential factor is proportional to root over of temperature. Okay, now is it clear? Okay, now is it clear, or anyone?
Yes, sir, clear.
Okay, thanks. So these three temperature dependency of exponential factor are actually
Sir,
important. Yeah, tell me.
hello.
Yeah, can you hear me? Yeah, sorry, I lost my connection. Yeah.
Sir, please repeat for collision theory.
Yeah, I had to repeat. Yeah, from collision theory, we have seen that we can write down the expression of rate constant. This is the rate constant K. So K will be equal to just pi r squared times average relative velocity times Avogadro number times exponential minus EA divided by RT, right? Now if you just replace R with sigma A plus sigma divided by 2, and the relative velocity V average will be equal to just root over of 8 kbt divided by pi mu. So then we can just in short we can write K equal to just AT, which is the pre-exponential factor, times exponential minus EA divided by RT, right? Now from collision theory, pre-exponential factor has this form, right? All these terms are inside the pre-exponential factor, so it will be pi times sigma A plus sigma B divided by 2 square times root over of 8 kbt divided by pi mu times n. So all these terms are inside the pre-exponential factor, right? This is pre-exponential factor. Now let's look at carefully. So this has this temperature dependent term, right? This pre-exponential factor has temperature dependent term. So we know for sure that in collision theory also the pre-exponential factor is temperature dependent, right? Now how it is depending upon temperature? It is the temperature is under the root, right? So that's why we are saying that the pre-exponential factor is proportional to root t. Okay, now is it okay, Sika?
Yes, sir.
Okay,
Yes, sir.
okay. Okay, so there are main take home message was the Arrhenius equation A was temperature independent. Transition state theory Eyring equation pre-exponential factor was temperature dependent and it was proportional to temperature. From collision theory pre-exponential factor is temperature dependent also and it is dependent as proportional to root t. Okay, so these are some basics and now let's move to the enzyme kinetics part. So basically in enzyme kinetics only one model which is very popular, which one is the Michaelis-Menten kinetics, right? So Michaelis-Menten. So in this model, so this is actually a model. So in this model, first let's say enzyme and the substrate, this E is for enzyme and S for substrate. So enzyme and substrate molecule will come together and form an enzyme substrate complex. Then from enzyme substrate complex the product molecules will form. So let's say the rate constant for the forward reaction is, let's say, K1. Rate constant for the backward reaction, that means from ES to reactant molecules, E plus S, is K minus 1, and rate constant for the enzyme substrate complex to product molecule is, let's say, K2. Okay, so this was the main model. Now from this model we have to find out the rate of enzyme catalysis reaction, that means K2. We have to find out the like dp dt. This is the rate. So how we are going to find out? So this enzyme substrate complex, so this enzyme substrate complex is actually an intermediate, right? So intermediate means it is very transient in nature, that means it has very low lifetime. So it has very low lifetime. So intermediate, transient intermediate, then we can use the steady state approximation, right? So we have discussed in the previous class, so we can use steady state approximation. That means we can write down as DES dt equal to 0. That means the concentration of the enzyme substrate complex will not change with time. So this is the steady state approximation. Now let's find it down. So DES dt will be equal to just K1 times E times S, right? Now E, enzyme substrate complex, is forming from enzyme and substrate with rate constant K1. So the DES dt will be K1 times E times S, right? Then it is enzyme substrate complex, also there is a backward reaction here. This reaction from enzyme substrate complex, enzyme and substrate are forming. That means the concentration of ES is decreasing. That's why the negative sign. So negative K minus 1 times ES, because from ES it is happening. That's why we have to write down the concentration of ES here. Now again there is another reaction, this reaction from enzyme substrate complex the product molecules is forming, that means with rate constant k2. So again minus k2 times es, right? So this is equal to 0, this is equal to 0. Now from this equation we can write down the concentration of intermediate es. So it will be equal to k1 times e s divided by k minus 1 plus k2. Okay. Now E equal to, so enzyme, so let's say at initially at time t equal to 0, E equal to E0. Now at any time t, so E plus es will be E0. So E will be just E0 minus es. So if you just put it here, k1 times E0 times s divided by k minus 1 plus k2 minus k1 times es times s divided by k minus 1 plus k2. So now the es concentration will be 1 plus k1 times s divided by k minus 1 plus k2, right, equal to k1 times E0 times s divided by k minus 1 plus k2. Okay. Now so es will be, now let's assume k minus 1 plus k2 divided by k1. This quantity ratio of k minus 1 plus k2 divided by k1, we call it km, which is Michaelis constant, right? So this is important. K minus 1 plus k2 divided by k1 is km. So again let's write it down, es times 1 plus kms, right, equal to E0 is divided by km, right? So es will be E0 is divided by km to 1 plus km is I think I have made some mistakes. Let me just check once. plus S.
Sir, please check for K2.
Yeah, K2 will be just K2 times AS. E equal to E0 minus ES, that is correct. Okay. Okay, let's leave it here. Okay, so basically I'm writing down the final expression. So basically the main point was k minus 1 plus k2 divided by k1. This quantity was Michaelis constant. Now E plus S equal to k1 k minus 1 ES k2 then P. So basically we are trying to find out this dp dt. So dp dt will be equal to k2 times ES. Okay. Now the final expression will be k2 times E0 times S divided by km plus S. Okay, now so basically the rate, so dp dt, that means the rate of the formation of product P. So it will be equal to just rate constant, some rate constant times substrate constant ES. Now if you just compare these two terms, so here rate constant will be equal to just k2 times E0. No, you cannot write this. Okay, this is in different conditions. So basically dp dt will be k2 times E0 times S divided by km plus S. Okay, now okay, this k2 times E0 is called Vmax. Okay, so that is the maximum rate Vmax will be k2 times E0. So E0 is the initial enzyme concentration, and often K2 is also called K catalyze. This is the turnover frequency. This is turnover frequency. It is also set K2 equal to K catalyst. So rate, that means V, will be equal to just Vmax times S divided by Km plus S. So this is the final expression, and if you just plot V with respect to the substrate concentration S, then you will get this type of plot. So this is the Vmax, this is Vmax, and half of Vmax, so let's say this is Vmax by 2. The concentration at which the rate is equal to the half of maximum rate, so this concentration is called the Km. that means Michael is constant. And also there is another Lineweaver-Burke plot which you can just, which is the double reciprocal plot. That means if you just take 1 upon v is equal to km plus s divided by vmax times s, so 1 upon v equal to km divided by vmax times s plus s divided by vmax times s, which will be 1 upon v equal to km divided by vmax times s plus this ss will cancel, 1 upon vmax. Okay, why double reciprocal? Because it is reciprocal of v here, 1 upon v, and reciprocal of s, 1 upon s. So that's why it is double reciprocal plot. This is a Lineweaver-Burke plot, 1 upon v versus 1 upon s. So this will be y equal to mx plus c types of plot. That means it will be a linear plot with slope equal to km divided by vmax, and intercept, this is intercept will be equal to 1 upon vmax. Okay, so from slope and intercept actually you can just calculate different quantities, like here slope, okay, slope will be equal to km means k minus 1 plus k2 divided by k1, and vmax equal to k2 times e0, and intercept equal to 1 upon k2 times e0. So from this quantity you can, from these two property you can just calculate different quantities like enzyme concentration, different rates, etc. Okay, so this was the main things that I wanted to say from the kinetics. Okay, so actually I think I made some mistakes from the mechanisms part. Okay, so but this was the final expressions, and I hope everything is clear. See,
Sir, please include numericals also.
yeah, so next class I will do the numerics from this kinetics chapter.
Okay, sir.
Okay, so any other doubts from this class, or?
No, sir. Thank you so much.
Okay, thanks. So in the next class I'll do mainly numerics, and let's say I'll also discuss some of the topics from equilibrium chapter. Okay, so today I'm just signing off. See you in the next week. Bye. Thanks for joining.